energy methods to find deflections in beams. Deflections can be determined by so many methods like double integration method, energy methods, area moment methods, column analogy method, even conjugate beam method. Okay. Out of all these, energy methods are more powerful and which follows like a standard procedure to find out the support reactions, even to find the deflections, slopes in the beams for both statically determinate as well as statically indeterminate beams. So in the energy methods, when you apply load on the structure, any elastic structure, we are doing some work on the structure. So this work will be stored in the structure in the form of the internal strain energy. Okay. So if there is no loss of energy, whatever the work we are doing on the structure will be stored in the structure as an internal energy. So by law of conservation of energy, the work done on the structure will be always equal to energy stored. This is the basic concept of the energy methods. Okay. These methods can be used to find the displacements or slopes. Okay. Let us see first what is how to find the energy stored. Let us take like a simple spring analogy which everybody knows. We know that the spring is a elastic member which will have some stiffness K. When this is subjected to a force along the axis, this spring will have a displacement x in the direction of the applied force. Then we are defining the stiffness as the ratio of the force to that of the displacement. Okay, F by x. Okay. K is the stiffness. So depends upon the direction of the loads. We got axial members, we got torsional members, we got a bending members. So every structure will have an axial stiffness, bending stiffness, torsional stiffness. So the work done here is always defined as the average force. What is average force? 0 plus F by 2. Because initially the force is 0, slowly we are increasing the force into the displacement x. This is the work done. So if there is no loss of energy, the work done will be stored in the structure as a internal strain energy. Once you remove the load, the internal energy which is stored will be relieved. In the process of relieving the energy, the spring will be taken back to the initial position. So all elastic members, they will store energy when they are loaded. Once you remove the load, they will come back to the initial position. Okay. It is just like a balloon. You pump air into the balloon will expand. Once you open the entrance, again the air will rush out. So the rushing of air will again take the balloon to the initial position. So all elastic structures will have a similar behavior. So I told you work done is equal to energy. So energy symbol is U. That U is given as F by 2 into X. But from this equation, what is F is equal to K into X. So that is equal to K into X, Kx square by 2. This is the energy stored in the spring. Okay. Similarly, if I take an axial member, when this is subjected to load P, this will have a small displacement delta L. For elastic structures, we know that this displacement is given by PL by AE. Okay. So this is for a spring. For axial member, the work done is equal to internal energy stored. That is, by definition, average force into displacement. This is the standard definition for the work done. that energy is given by P by 2 into delta L is PL by AE. That implies P square L by 2AE. This is the energy stored in the axial member, where L is the length of the member, A is the cross section, because this member may have some cross section. Okay. E is the Young's modulus, or the strength of the material due to the axial loads. Okay. Suppose if I take a small elemental length here, dx, a distance equal to x from this, the elemental energy delta U is given by P square L by P square L. Here the L is now dx. P square into dx by 2E. Then what is the total energy? The total energy is always integration, that is delta U. That's equal to P square into dx by 2A. Okay. This is the energy stored. Now see, the energy stored is square of the load. That means if the load is tension or compression, that means load is positive or negative, it is a square of the load. Square of the load. So the energy will be always positive quantity, irrespective of the direction of the load acting on the structure. So total energy means integrate from 0 to L, because here x is equal to 0 and here x is equal to L. So that now we'll get the total energy stored in the structure. P square into dx by 2A. Okay. See, if this is the displacement, then what is the stiffness of this member? That is called axial stiffness. The stiffness is always defined as load by displacement. That is P by PL by AE. So therefore, the axial stiffness of this member is AE by L. Okay. See, the axial stiffness of the member will not depend on the applied load. It only depends upon the geometry of the given material and the material property, like a Young's modulus. A, cross-sectional area, L, length of the structure. So both are geometry only. So remember, the stiffness always depends upon geometry and material property, not on the load. Okay. This is the axial member energy stored. Then the third one. Okay. Suppose if you take a shaft. Okay. This is the shaft. I am fixing this end. Fix this end when this is subjected to torque. Torque T. Okay. So now because of torque, what happens? These cross sections of the shaft will try to rotate tangential to the surface. Okay, resulting in torsional shear stress. So that if I take a small element here, this layer will displace to this layer, so that the cross section rotates an angle theta. Okay, so here the work done is defined as the average torque. What is the average torque? 0 plus T by 2. Because suddenly we will not apply the torque. That's why in the energy conditions, always take the average load. Average torque into angle of twist. Okay, where theta is the angle of twist, which is given by TL by GG. Okay. Now, the energy is equal to work done. If there is no loss, that becomes T by two into theta, that is TL by GG. You know, where G is the the torsional modulus of the shaft material. J is the area polar moment of inertia. L is the length. T is the applied torque. These things we learned in the torsion chapter. So that is given by T square L by 2GG. If we keep this in integration format, that becomes integration of T square into dx by 2GG. Okay. So here also, whether the torque is clockwise or anti-clockwise, the energy will be always positive quantity because the energy is a square of the applied load, that is torque. Okay. Right. Now, the torsional stiffness KT is defined as torque by angle of twist. Okay. The axial stiffness, what we are defining, load by displacement. Similarly, the torsional stiffness is defined as torque by angle of twist. That gives GJ by L. See, the torsional stiffness KT is also a function of G, material property, J, geometry, that is like a J is equal to how much? Pi by 32 d power 4. L is the length of the shaft. Okay. Now, the fourth case is beams. Suppose you take a cantilever beam. When this is subjected to bending moment M, the beam bends like this. Okay. See, this cross section before loading straight, after loading also straight, but undergoes an angle of rotation theta. That is called slope of the beam. Then the work done on the structure due to bending is defined as average bending moment by 2. This is the average bending moment into the slope of the beam. Okay. So when a work done is equal to energy stored, that is m by 2 into theta. The slope of the beam is given by ml by ei, where E is the Young's modulus, I is the area moment of inertia, L is the length of the beam. These things are standard, which are already discussed in other topics. Okay, that is given by ml by ei. Okay, so when you keep this in integration format for a small element length, it becomes m square into dx by 2ei. This is the bending strain energy. Okay. Then what is the bending stiffness KB? The bending stiffness is always defined as the ratio of load. Here the load is bending moment only by the slope theta. That gives EI by L. This is the bending stiffness. Okay. See here we got first we discussed with respect to the spring and we understood what is the energy stored. Then we applied the concept to the axial member. Then second torque member, torsion member. The third one is the bending member. This is the cantilever structure subjected to bending moment. Okay. Now this is the bending energy. M square into dx by 2ei. So suppose this is the elemental length. We have taken here a distance equal to x. This is dx length. So what is the limit of the x? Here at the free end, x is equal to 0. All the way for the entire structure to the fixed end, x is equal to L. So the total energy means 0 to L. This is the total energy stored due to the bending moment in the structure. Okay. Remember this. Now, once we know the bending energy in the structure, we can find the deflections. Okay. as well as slopes. So the deflections and slopes for the beams based upon the energy concept is given by Castiglia Theorems. Okay. Castiglia's theorems. He said given like two simple theorems to find the slope and deflections. When a structure is subjected to, suppose if there is a structure which is a random cross section, or when there is a load acting here, okay, at the point of loading we'll have some displacement, okay, or suppose if you are applying a load here, say like I am applying a load P here, so that the beam undergoes displacement or deflection like this. Why? Why is the deflection? Theta is the slope. He said, once we know the total energy stored in the structure, he said, the deflection under the load is given by Y, is given by the partial derivative of total strain energy, the partial derivative of the total strain energy with respect to load at that point. This is the first statement given by Castiglia. Okay, remember that. Once we find the total energy stored in the structure, if you want to find deflection under the load, okay, deflection under the load, he said the deflection under the load is given by partial derivative of total strain energy with respect to load at that point. Okay. By using this equation, we can find the deflection. Then the second statement he made is the slope under the load is given by, the slope, that theta is given by the partial derivative of total strain energy U with respect to bending moment at that point. Okay. This is the second theorem by the Castiglia. Okay. The first one is deflection. The second one is slope. In this case, where U is the total energy stored in the structure or in the beam. Okay, it must be the total energy in the beam. Okay, then P is the point load. Other name is concentrated load. Or other name is discrete load, because in the numericals they will use different words different times. Discrete load, where M is the bending moment. Okay, right? These are the two equations proposed by Castiglia. So you must know first how to find the total energy in the structure. Once you know the total energy, we can find the deflection and slope by using the equations 1 and 2 proposed by Castiglia. This is theorem 1. This is theorem 2 for the slope. Okay. Now you will have here serious doubt. What if there is no point load at a particular location where we want to find the deflection? Okay. Say this is a structure where the load is applied here, P. But you want to find the deflection somewhere along the span, say like a distance equal to L by 2 at the center of the beam. Then what you do is, suppose this is the C point, this is B point, this is A point. Here apply the dummy load Q. Okay. Then find the energy. The total energy is energy in the portion AC plus energy in the portion CB. This is the total energy in the structure. Then, so these energies UAC, UCB are functions of P, Q and material property, that is EI and L. Okay. Once you know the energy, then you want to find the deflection at C point. The deflection at the C point is given by partial derivative of total energy with respect to load at that point, that is dou Q. Okay. Then finally set Q is equal to 0 because Q is actually not there. Okay. So that's why this is called Q here called dummy load. Q is called dummy load, also called as a imaginary load or fictitious load. Okay. Now, if you want to find, say, like a deflection at a B point, YB, that is given by dou U by dou P, because already there is a point load, but here P is not equal to 0 because P is the actual load. Okay. By using this equation, we can find the deflection at C point. By using the second equation YB, we can find the deflection at a free end. Okay. Similarly, if there is a no point load, but UDL as well as uniformly varying loads or moments are acting, then how to find? There also, we can apply the imaginary point load, find the moment at that point, find the total energy, then differentiate the total energy with respect to the load at that point. If the load is imaginary load, set the load to 0. You will get the answers. Okay. This method is quite convenient and comfortable. Any kind of structural problems can be solved by this Castiglia's theorems because the energy methods are very powerful compared to other methods because these are latest methods. Okay. Okay. Now, see, the energy is given by m square dx by 2 EI. Then what is the deflection? Y is equal to dou U by dou P. We can express this in a different style also. Differentiate this with respect to P. Differentiate the energy with respect to the load. That becomes dou M by dou P. That becomes 2M into dou M by dou P by 2 EI into dx integration 0 to L. 2 gets cancelled. Therefore, the other way is directly if you know the moment, that is M by EI into dou M by dou P 0 to L into dx. This is the another form of the equation to find the deflection. Okay. Once you know the moment, you can differentiate the moment with respect to the load at that point so that you will get dou M by dou P. Substitute that and then carry out the integration, you will get the deflection. Okay. Then what is slope? The slope is dou U by dou M. That is, when you differentiate this with respect to M, integration of M square becomes how much? 2M. 2 gets cancelled. You will have an equation m m dx by EI, 0 to L. This is the slope equation. Okay. So you can remember these equations either in the standard format or as a function of the moment and load, like this. Now let us take some examples to clarify this Castiglia's theorem. See how simple it is. Because if you want to find the slope and deflections by the double integration methods, you have done like a lot of lengthy procedure. First, we have to express the moment equation. Then we have to carry out the integration twice. By substituting the boundary constants, we have to find the constants of integration. So like a lot of lengthy procedure is there, whereas this gives answers in a simple manner. Let us see the case 1. Okay. A cantilever structure. I am taking. Fix this. Okay. This is the structure. Now, this is subjected to a transverse load P, where L is the length of the structure. Anyway, EI, the flexural rigidity, is always constant. Okay. Question is, determine the deflection at the point where the load is acting, that is at the free end, A, B. Okay. Question is like this. A cantilever beam of length L, flexural rigidity EI, is subjected to a transverse load at the free end. Determine the deflection and slope at the free end. Okay. Even they can extend the question. Also find the bending stress. Okay. Let us see. Or even the question can be extended. Also find the shear stress. So let us see the solution. Okay. When I take a section here, a distance equal to x. Okay. Now this is the free body diagram. The load is acting down. To keep this element in equilibrium, there must be a force F upwards called the shear force. So that because of the F and P, the force is balanced, but since they are separating by distance x, this will try to rotate clockwise. To prevent the rotation, there must be a moment anti-clockwise like this. So that the moment is defined as P into x. Okay. Then what is dou m by dou p? X only. When I differentiate the moment with respect to load, you will get dou m by dou p as a x. Therefore, the deflection y is given by m. How much? Apply this formula. Okay. P into x by EI into dou m by dou p is x into dx. Carry out integration from 0 to L. X into x becomes x square, that is P by EI x square dx. Okay. Limit 0 to L. Therefore, y is given by x square integration becomes how much? X cube by 3. P by 3 EI. The limit is x cube 0 to L. That gives PL cube by 3 EI. See here. We got answer in like 2 steps. Whereas a double integration method will take more time. Okay. This is the deflection. Then what is the slope? The slope is given by integration of, see here, slope is given by m by ei into dx. M is p into x dx by ei 0 to L. When you carry out this integration, x integration becomes x square by 2. When you substitute the limiter, you will get PL square by 2EA. We have seen the same answers by the double integration method also. Okay. Right. These are the slopes and deflections. Okay. For a cantilever beam. Okay. Now we'll have a doubt. Suppose you want to find the deflection at the center of the beam here. The distance equal to x is equal to L by 2. How? That we'll see in the next case. Let us see the second case. Suppose there is a cantilever beam. Okay. Now this is subjected to uniformly distributed load of intensity W per unit length. See here, for every beam, the length and flexural rigidity will be constant. Okay, I don't have to show every time. L is the length, EA is the flexural rigidity. The question is, find the maximum deflection. We know maximum deflection occurs at the free end of the structure. But since this is a UDL, there is no point load. Okay. Question is, determine maximum deflection, comma, slope is the question. Okay. Let us see the solution. For this kind of structures, if you want to find the slope and deflections by the energy method, since there is no point load, you apply a dummy load here. Generally, the dummy load is shown by the dotted line. Q is the dummy load. Dummy or fictitious or imaginary load. Okay. It's called by so many names. So first you take a section here, a distance equal to x, so that this is the element, the load here is q. This w into x will act at the center of the beam, that is wx, a distance equal to x by 2. Okay. Now here we'll have a shear force, we'll have a bending moment. Now what is the bending moment here? The bending moment is Wx into x by 2 because of UDL, which is a clockwise, plus q into x. Okay. Then what is dou m by dou x? Sorry, dou m by dou q here. Dou m by dou q means when I differentiate this with respect to like a q, this term will be 0, whereas this here will have only x. Okay. But actually there is no load. That means q will be equal to 0. When q is 0, what is the moment? The moment becomes Wx square by 2. Okay. Now apply the formula, that is y is given by integration of m by ei into dou m by dou q into dx. Okay. That is 0 to L. So that's equal to m is Wx square by 2 into dou m by dou q is x into dx by ei integration 0 to L. This is the deflection. So x square into x becomes how much? X cube. So w by 2ei into integration of x cube dx 0 to L. X cube integration becomes how much? X to the power of 4 by 4. So 4 into 2, 8. W by 8 ei into L power 4. This is the deflection. Okay. The same answer we got even by the double integration method also. Okay. This one. Suppose you want to find the slope. What is the slope? M dx by ei 0 to L. That's equal to m is Wx square by 2 into dx integration 0 to L. Okay. So that if you carry out this integration, the slope is given by x square integration becomes x cube by 3. 3 into 2, 6. Substitute the limiter, that is WL cube by 6 here. This is the equation for the slope. Suppose you want to find the total energy. What is the total energy? U m square dx by 2e. Substitute that. M square means W x square by 2 whole square dx by 2e. See, 2 square means here how much it becomes 4. 4 into 2, 8. W square by 8ei into x square into square, that means x to the power of 4 integration, that becomes L to the power of 5 by 5. So that the total energy in this structure is W square L power 5 by 40 EI. This is the energy stored in the structure. Okay. Right. So, numericals. They may give the length, they may give the Young's modulus, they may give the moment of inertia of the cross section. Okay, the load will be given, from which you can find the deflection, you can find the slope, you can find the energy. This is the deflection, equation number 1. This is the slope, equation number 2. This is the energy. Okay. This way, the energy methods are more powerful. And it's you don't have to remember by heart anything here. It's only purely based on the concept. Okay. Only thing is you must be careful while taking the moment and then applying the equations. say third one. Okay. The third one is, now I'll go to like a little big question. This is the cantilever beam. Now we are applying load here, P, at distance equal to X. This is already we have done by the method of superposition. Okay. Even by the energy method also we can do it here. A, B, C. For this cantilever structure, the question will be determine the maximum deflection. Okay. We know that the maximum deflection occurs at a C point only, at the free end. Question. Determine the maximum deflection. Okay. Right. So, solution. See, the other question will be like as standard format, like a cantilever beam of length L, okay, is subjected to a point load at the center as shown in figure. The flexural rigidity of the entire beam is constant. That is, he said EI is constant. Determine the maximum deflection. Okay, that means we have to find the deflection at the free end. Solution. Maximum deflection occurs at the free end. Okay. Maximum deflection occurs only at the free end. That means at the free end, what we have to do? We have to apply the dummy load. Say here the load is P, here the load is Q. Okay. A, B, C. What is the next step? First find the total energy in the beam. What is the total energy? Energy in the portion AB plus energy in the portion BC. Okay. This is the total energy. So what is like a YC? YC is equal to dou U by dou Q. Differentiate the total energy with respect to load at the point. That becomes, see, if I write the energy equation here, this is MAB square dx by 2EI plus MBC square dx by 2EI. This is the energy in the portion BC. Okay. Then when I differentiate this with respect to Q, what the formula becomes? This is MAB by EI into dou MAB by dou Q into dx plus MBC by EI into dou MBC by dou Q into dx. Okay. So now, if this is L by 2, this also will be L by 2. Okay. So we can start a moment equation from the right hand side, from the free end, and we can move to the fixed end. Suppose if I take a section here at distance equal to x, what is the moment between B and C? We know that MBC is Q into X. Okay, Q into X. Then what is dou MBC by dou Q? That must be X. Okay. But here Q is a dummy load. Remember, that means Q will be 0. When you set Q 0, what happens? MBC, this entire thing will be 0. That means this entire limit will be 0. Okay. Now, see, starting from B, if you take moment, starting from the B point, so this is already L by 2. If I take a section here, a distance equal to X from the B, what is the moment here? MAB is equal to Q into X plus L by 2. Q, force into perpendicular distance. This is L by 2, this is X. Q into X plus P into X. Then dou MAB by dou Q. How much it becomes? X plus L by 2. But actually Q is a dummy load. So what happens? This term will be 0. Okay. This term will be 0. Now substitute the values. Therefore, YC is equal to integration of dou MAB. How much? P into X by EI into what is dou MAB by dou Q? X plus L by 2 into dx. Okay. Now here, see, we are measuring the X from B point. From B to the fixed end, what is the limit? 0 to L by 2. You must be careful from where we are taking the distance. So we have to apply that integration limit into the equation. So if you solve this integration, that is P by EI integration of X square dx plus L by 2 into X dx. Okay. 0 to L by 2, 0 to L by 2. That is P by EI into X square integration becomes how much? X cube by 3. That is L by 2 cube by 3 plus L by 2 into X integration becomes X square by 2. That is L by 2 whole square by 2. So that the YC becomes 5P L cube by 48 EM. This is the deflection at the free end. Okay. This is by the energy method. Okay. Now the energy methods can be applied to the beams as well as even to the frames also. Okay. Now let us see one more example. The fourth one. Simple supported beam with the eccentric point load is the question. Question is like this. There is a simply supported beam supported here, supported here. Now this beam will have some cross section, maybe a rectangular cross section. What are with the cross section? For that you can find the I value. Material will be given so that we can find E and I. Okay. Now this is subjected to a point load P, say a distance equal to A from the left hand side, B from the right hand side. Now we have to find out the total energy in the beam as well as the load under the deflection under the load. This is A, B, C point. Okay. Question. Determine total energy stored and deflection under the load. So these are the two important values required for a structural design. Okay. First, you have to see what is the maximum energy stored, what is the deflection. Even from that, you can find the maximum deflection also. Okay. Let us see the solution. For any simple supported beam, first we have to find out the support reactions. Say, this is the beam. I hope all of you know how to find the support reactions. We have done in the previous sessions. Say, this is RA, this is RB. This is A, this is B, where L is equal to A plus B, total length of the beam. When I take moment about point A, which is equal to 0, that is P into A clockwise moment minus RB into L anti-clockwise equal to 0, from which we can find RB is equal to PA by L. Similarly, RA is equal to PB by L. Okay. Both are vertically upwards. Then, the energy in the structure U is given by energy in the portion AC, because energy in the portion from A to C plus from energy in the portion C to B, so that we get the total energy in the structure. This is the total energy. Okay. So that is given by, as a function of moment, mac square dx by plus mbc square dx by 2ei. This is integration where from A to C, what is the limit of integration? 0 to A. Here the integration becomes 0 to B. Okay. Right. Now, what is the moment equation from A to C? If I take a section here, a distance equal to x, the moment is equal to force into perpendicular distance. That is mac is equal to, see, this gives a clockwise moment. Clockwise moment generally will take positive. That is RA into x. RA is PB by L. PB by L into x. Then, what is the moment in the portion BC portion? From this side, we can take a moment here. From this, a distance equal to x. The limit is here, x is equal to 0. Here, x is equal to b. Here, the limit is x is equal to 0. Here, the limit is x is equal to a. So that the entire beam is covering. So, the total energy is, what is the MBC given here? P A by L into x. Since this is like an anti-clockwise moment, we can keep negative here. Okay, this is anti-clockwise. This gives anti-clockwise moment. This gives clockwise moment. From this side, it's a clockwise. From this, it is a anti-clockwise. Anyway, the sign convention does not matter here because the energy is a square of the moment. So that this is ma square, that is pbx by L whole square dx by EI plus this is mbc is pax by L minus whole square dx by EI. So what is the limit of integration here? 0 to a. Here the limit of integration is 0 to b. When you carry out this integration, I'll take the common terms first out, that is p square by L square EI constant. This is b square x square dx plus this is a square x square dx. Limit 0 to a, 0 to b. Okay. If you carry out this, you will get p square, a square, b square by, see here, x square integration becomes how much? 3. Okay. Just this is x square means x cube by 3. But here 2 is there, so 2 term also will be there common. 2 into 3, how much? 6 L square EI. A square b square into this is x square. When substitute the limit, how much it becomes? A cube. This how much becomes? B cube. This is the value. Okay. But you know, L is A plus B, no? Okay. No. Wait. It's a integration will be, this is b square and x square becomes how much? A cube plus this is a square, limit becomes how much? B cube. Now you can take a square b square common. A square b square, this is a plus b common here by 6 L square EI. So we know a plus b is nothing but L only, so 1 L gets cancelled. The total energy U in the structure is given as p square into a square b square by 6 EIL. This is the total energy. For a simple supported beam with eccentric loading, eccentric point loading, the total energy is p square into a square b square by 6 EIL. So, since we want to find the deflection under the load, now you directly can apply the Castiglia's theorem. What is the Castiglia's theorem? The partial derivative of total energy with respect to load at that point gives deflection at that point. Therefore, when you differentiate that with respect to the load, that is p square, a square, b square by 6 EIL. P square differentiation becomes how much? 2p. 2p means 6 goes 3 times. That is p into a square b square by 3 EIL. This is the deflection under the load. Remember this formula. Okay. Or we can find the deflection even from the basic moment equation also. Or first we can find the energy, differentiate the energy with respect to load, you will get the deflection. Note here. Suppose if the load is applied at the center of the beam, okay, if the load is applied at the center of the beam, that is A is equal to L by 2, B also L by 2. Okay. Now it is not eccentric, it is a centric load. Load at the center. So then the deflection becomes maximum. That is, Y max is given by P into L by 2 whole square, L by 2 whole square by 3EI into L. Okay. So 4 into 4, 16. 16 into 3, how much? PL cube by 48E. This is the maximum deflection when the load is acting at the center of the beam. Okay. So, if the numerical values are given, the cross section is given, load is given, length is given, Young's modulus will be given, I value you can find out, then you can find the maximum deflection at the center. Or if the load is eccentric, by using this equation, we can find the deflection. Okay. Or if they ask you to find the energy, you can find here. Okay, now what happens energy here? The energy will be U is equal to, that becomes P square L cube by 96 EI. This is the energy when the load is acting at the center. So that when I differentiate this, we'll get the same PL cube by 48 EI. This is the energy stored. Okay. Energy stored when the load is acting at the center. When load is acting at center of beam. Okay. Right. Now, let us see some frames. Deflections in frames. Okay. Suppose there is a L frame like this. There is a L frame. This frame is hinged here. This frame is hinged here. Now we are applying a load here, P. Here they kept a roller. A rigid roller is kept. Okay. This leg got a length L. This leg also got a length L. This is O, A, B. Okay. When you keep the frame like this, and apply a load here, this frame will try to bend down. Okay. So that at A point will have a deflection. For this structure, EI is constant. Here, sometimes it need not be constant. This member may have a different EI, this member may have a different EI. Okay. If they are different, we can find that by incorporating the given values. Now, when apply load here, see, this B point will try to rotate clockwise. This will try to rotate clockwise, but the roller is opposing. So, the roller will induce a reaction R here. Okay. The roller will induce reaction R here. When I take moment about the hinged point, sigma MO0, that is P into L clockwise minus R into L anti-clockwise, because this is giving clockwise moment, whereas this gives anti-clockwise moment, equal to 0. Therefore, R is equal to P. Now, so this is also equal to P. See, the length is same, A is constant. Okay. Therefore, the total energy U is equal to energy in the portion OA plus energy in the portion OB. Since the loads and geometry and material is same, the energy in the portion OA will be equal to energy in the portion OB. This I can write as a 2 times energy in the portion OA portion. This is the energy that is given by 2 times. What is energy? Suppose if we take a section here, a distance equal to x, where x is equal to 0 here, x is equal to L up to the O point. The limit of integration becomes 0 to L. The moment MOA whole square dx by 2EL. This is the total energy stored. Therefore, U is equal to 2 times, what is the moment here? P into x, clockwise moment. That is Px whole square dx by 2EI. That is 0 to L. Okay. When you carry out this 2 goes to cancel, that is P square into x square integration becomes how much? X cube by 3. Substitute the limit. That is L cube by 3EI. This is the total energy stored in the structure. Okay. See, at R point, there is no deflection because the roller is opposing the B end to move towards like a right. So, we will have only deflection at A point. At A point, there is a load is there. So, therefore, YA is equal to partial derivative of the total energy with respect to load at that point. That is given by how much? 2P L cube by 3EI. This is the deflection. Okay. If you see how the frame undergo bending, there is like a elastic curve. Okay. I will show the elastic curve. See here, this end is not moving. So, this will try to bend like this. Then from here, it will bend like this. Okay. So that this is the deflection at this point YA. Okay. The structure deflects. So if you show only the axis, that is called elastic axis of the beam after bending. It will be in this form, in this manner. Right? Okay. Now, suppose the same question they can ask like this. say this is the frame. Instead of hinging here, now it is fixed here. It is fixed here. This length is L. This length also L. Now there is a point load P acting here. Here also, anyway, same frame. That means EI is constant. The question is, determine the deflection at the free end. Okay. See, when I apply load here, this load, when I transform to here, so the load will act down, followed by a moment. Okay. Let us see the solution. Okay. This is O, A, B. We call it like that. We have to find out the deflection at B point. Then we have to find out the total energy in the frame. These are the two kinds of questions. Okay. A L frame which is fixed at one end, subjected to loading at the free end as shown in the figure. Determine the total energy in the frame and deflection at the free end. Okay. Let us see. We know the energy is equal to energy in the portion AB plus energy in the portion AO. This is the total energy in the structure. So when I take a section here at distance equal to x, we can get moment between A and B. When I take one more section here from A to O, okay, we'll get a moment in the portion OA. Okay. That is MAB square dx by 2AE plus M OA. This is OA square into dx by 2AE. No, sorry, it is a beam. So it must be not the axial rigidity, it is a flexural rigidity. Then what is the moment in the portion AB? That is P into X. Okay. When see the load I can transfer to this point, there is an axial load P followed by a moment. What is the moment here? P into L. So when I take a section here at distance equal to X between O and A, the axial load P will not cause any moment. Only got a constant moment PL. Therefore, the moment in the portion OA is equal to constant, that is P into L. Right. Now find the energy. U is equal to MAB is Px whole square dx by 2EI. The limit of integration is 0 to L plus, here this is PL whole square dx by 2EI. So that energy becomes, anyway this is P square, I can take P square by 2EI common. X square integration becomes x cube by 3. L cube by 3. Here L square into x integration becomes, this also 0 to L. That is dx integration becomes x, that is L. So when I cross multiply, that becomes 4 P square L cube by 6CI. This is the total energy, that is 2 P square L cube by 3EI. This is the energy stored in the structure. Okay. So, what is the deflection? The deflection YB. Already there is a point load. So, partial derivative of the total energy with respect to load. That is dou U by dou P. That becomes 4P L cube by 3EI is the answer. Okay. Now see how it will deflect. What is the elastic curve for this? See, because of this moment, the beam will try to bend towards like a left side. Okay. See the elastic deflection, elastic curve. The beam deflects like this. Okay. So that this is the deflection at a B point. Okay. Even we can find the deflection at A point also. Here also, because there is a horizontal deflection. Okay. If you want to find the horizontal deflection here, we have to apply a dummy load. Then only we can find the deflection at a point also. Horizontal deflection. Okay. I'll show that also. Okay. Right. The question is, for the above frame, determine the horizontal deflection at a point A. Determine the horizontal deflection at A. Because anyway at A point actually there is no horizontal vertical displacement. Why? Because the axial load will cause tension and stretching of the member, but we are neglecting the axial deformations. We are neglecting the shear deformations. Okay, those things will be mentioned very clearly in the questions. Okay, while we are studying the bending effect, mostly we will neglect the axial effect as well as shear effect of the structure. So, if you want to find the axial, horizontal deflection at A, what you have to do? Again, same procedure. Suppose this is the structure. Okay. Apply the dummy load here. Okay. This is the dummy load Q in the horizontal direction. Then, so this is O, A. This is B point. This is the load P here. Okay. Then what is YA? YA is equal to dou U by, because find the total energy in the structure, differentiate that with respect to the load at that point. That is by dou Q. Dou U by dou Q. Finally, we can set Q is equal to 0 because Q is the dummy load. Okay. What is U? U is OA plus AB. UAB plus UAO. Okay. That is given by M AB square dx by 2EI plus M BC square dx by 2EI. So that YA, the deflection at A, is dou U by dou Q. So when you do that, that is MAB, dou MAB by dou Q by EI into dx plus MBC sorry, it's a OA. MOA by dou MOA by dou Q by EI. Anyway, both got the same length, so the limit of integration becomes same, 0 to L, 0 to L. If they are given different lengths, you can take the integration of that corresponding length. If they are given two different cross sections, you can take the flexural rigidity of that section. Okay. Right. So first you find out, take a moment at between like AB. What is MEAB? That is P into X. But what is dou MAB? This is AB by dou Q, that is 0. So since this term is 0, this entire term will be 0. Okay, because dou MAB by dou Q we got 0. So only left out only this term. Now when I take moment here, okay, the moment here becomes, so this is P into L. Here the moment is P into L plus Q into X is there. That means MOA is equal to QX plus P into L. Then what is dou MOA by dou Q? That becomes X. But actually Q is dummy load, so this term also becomes 0. Now substitute that. Therefore, YA is equal to dou MAB because this is dou MOA, no? Sorry, dou MAB by dou Q is 0. So this term will be 0, not this term. Okay. So substitute that. PL into dou MOA by dou Q is X by EI into dx, 0 to L. That's equal to PL. X integration becomes how much? X square by 2, that is L square, that is L cube by 2EI. This is the deflection at a point which is horizontal. This is horizontal deflection at a point. Anyway, there is no vertical deflection because there is no like bending or like display load in the vertical direction. Okay. But because of the axial load, we'll have axial deformation that is anyway neglected. Now, you know the deformation already, the elastic line of this structure I have shown in the previous case only. Okay. This way, whatever be the kind of the structures, we can find the total energy stored, we can find the deflection under the load, or anywhere if you want to find the deflection, at that point, you apply the dummy load, then apply the procedure. Finally, set the dummy load to 0, evaluate the equations, you will get the answer. Okay. We'll continue this in the next class.
Like, share and subscribe. Hit the bell icon for more updates.